Okay, hi, I'm Roger Clark. I'm a co-investigator on the EMIT mission. EMIT is Earth Surface Mineral Dust Source Investigation and Imaging Spectrometer that is on the International Space Station. EMIT was launched on a SpaceX Falcon 9 to the ISS on July 14th in 2022. It started operations a short time after in August, and we've been in operation for most of that time. There was a short fall of 22. We were off due to a power supply issue on the space station that was ultimately fixed. So we've passed our prime mission, or up to the end of this month, and we're go for extended mission for to 2026. As most of you know, anybody who's been working in spectroscopy know that spectra does senses composition, and composition can be applied to all kinds of problems. And here just a few are listed for the Earth system here. These same things, at least the geology and snow and ice physics, apply to other planets. We haven't found the ecosystems yet, but that's a potential too. Climate, besides surface detail, EMIT is sensing the surface, but we also sense the atmosphere, and you can do atmospheric physics also. And I'll show an example of that. The EMIT mission was is a cost cap mission. It's an expanded and extended mission, but in the prime mission, the goal was to map the minerals in arid regions that get lofted into dust storms and influence radiative forcing in the climate system and the effect on climate change. And we've achieved those goals. It's actually quite spectacular. And the radiative transfer models and the effects are being calculated now. As soon as that's all verified, those will all be delivered and the data public. All the data from EMIT is made public within a short time of acquisition, and that can vary from hours to a couple of days typically. If it stretches out to a couple of days, it's probably because we've collected so much data. There's a backlog of pushing it through the pipe to the Aeros data center. But it's very rapid in general for getting the spectrum. So EMIT is being on the ISS. It's constrained to observe what is underneath the ISS, which is, I forget the exact inclination of the ISS, but it's around plus or minus 50 degrees, 52 degrees maybe, if somebody remembers that. The ISS orbit also varies from nominally about 400 kilometers high, but it can go up and down 40 or 50 kilometers, about that mean. So the image cubes or the footprint that EMIT has is about a 60-meter pixel. We chop the data up into 1242 wide and 1280 pixel long scenes. There are some exceptions there, but that's the standard image cube, and this is an example of an image cube here. Can everybody see my cursor so I can point to things?
Yep, we can see them.
Okay. So being an imaging spectrometer, working in the visible to shortwave infrared, it goes from 0.35 to 2.5 microns. Very good spectral resolution, and these are example radiant spectra. The radiant spectra are delivered, so it includes the atmospheric transmission and the solar spectral response. And we also deliver a apparent surface reflectance. That's surface reflectance of the surface, assuming it was horizontal. We don't take into account topographic slopes. So these are example mineral spectra or surface spectra that show minerals. The blue curve here that shows hematite, and the red curve is shifted longer. That's agarthite. And over here we have carbonates in green and phyllosilicates in the blue and red. So the these are the minerals that are of concern to EMIT for radiative forcing. And what we know, for example, that iron oxides in dust are more absorbing in the visible, and that tends to create a warming effect. And if they're iron oxide poor, they're bright in the visible, and most things are bright in the infrared. So we reflect more sunlight and it cools the atmosphere. So depending on the mineral composition, you can get in a dust storm cooling or warming of the atmosphere. And the EMIT project will quantify that and the magnitude and direction, cooling or warming for the global system. To do that, EMIT, we get the spectra. And by the way, these spectra over here, the surface spectra, now this slide was given to me by Rob Green at JPL. So I don't know if these are averages, but when I extract spectra from single pixels, most single pixels look this good. They look like lab data. Now, there's 2 gaps in here. That's due to the 1.4 and 1.9 micron terrestrial water bands, where the water is abundant enough and the absorption strong enough that it's opaque looking through the atmosphere, except maybe on the very tallest mountains. But for most of the Earth system, it's too opaque to get any usable signal through here. So these are just gaps in the data. That limits, we could do composition work here if we had these wavelengths. And on other planets like Mars, we with the CRISM instrument, that's, well, it's not taking data now, but when it was taking data, and there's a lot of data out there, we can do search for water using 1.9 micron water band, for example, and clays and OH bearing minerals in the 1.4 micron region. So the EMIT instrument was started, the build was started a little before COVID. So COVID stretched out delivery some, but it's a state-of-the-art imaging spectrometer and was delivered in 41 months despite COVID. And you can see here from the size, it's about the size of a kitchen oven. It has about a little over a 4-inch, 110 millimeter aperture telescope. It's a innovative new design for an imaging spectrometer, and there are advantages to that. By the way, the same design spectrometer is what's on the MISE instrument on Europa Clipper going up to the Jupiter system in October. It uses a Dyson lens, a calcium fluoride Dyson lens. And the reason for this unusual design is to reduce the optical aberrations. So it's a very fast system, f1.8, and you can see here the cross-track pixels are aligned very well. Other imaging spectrometers have what's called spectral smile. So every column pixel has a different wavelength, and that adds complication for analysis. And simplest is to resample the data, but people generally don't like to resample the data. They like to work with the fundamental spectra, but then you have to track all those different wavelengths at one time, and that makes it more difficult. So EMIT is, with this new design, I'm just floored at how good it is. I mean, it's like lab data in space. Being on the ISS, this shows our coverage, our limits of the orbit here. I think that's around 52 degrees, the top of the United States here is 49 degrees, so a little bit more than that. So we do not get the polar regions, unfortunately. AVRIS, which is an imaging spectrometer flown by JPL on various aircraft, has gotten data up there. So if you need data at the higher latitudes, check and see if AVRIS data are available. I know they recently flew Iceland. We've been studying Iceland some. You can see these are the blue areas are the areas covered so far in just a little over a year. You're taking out the time we were off, maybe a year and a quarter of data taking. And we do have cloud screening, so we don't download the data to reduce the data volume and the data rate coming down. So if a scene is cloudy, we don't download it. So these are at least partially, if not completely, cloud-free scenes. And you'll see examples that still have a few clouds in them. But 70,000 cubes as of the last couple of weeks. I don't know exactly when that is, but it's quite a lot. And with extended mission, we're going to get more and more coverage. So let's see, the science goal, as I've already said, is to discuss the heating and cooling of the Earth. But now that as we go into extended mission, several new investigators have been added to the team. We haven't gotten together yet, but we will in the next month or so, and it'll expand the science operations. The current global mineral, not global, but arid region minerals that have been derived from the EMIT data, and that uses the touch-quarter system that I've been working on for a large part of my career, and is in operation at JPL on a Beowulf cluster. And it's the same system with the same software, same expert system for identifying minerals that we used on the TREX project with the TREX rover in the field. So this is a global map that shows where we've covered the arid regions with 3 minerals: hematite in red, goethite in green, and kaolinite in blue. And this is an RGB composite. And the next image shows North Africa in a little more detail. And this is obviously, it's been reduced to the full resolution. The full resolution is, tens to hundreds of thousands of pixels across, so it's hard to show on a single image. But the diversity of mineralogy and the complexity of patterns is unlike anything I've seen from an imaging spectrometer on any other moon or planet. So Earth is quite unique in this regard. There are other applications, and one of the applications that was funded separate from the EMIT team for the climate change work was the search for point sources of methane and also carbon dioxide. But the methane has been the big attention getter at NASA headquarters, and certainly helped us with extended missions, showing what many of us already knew, that imaging spectrometers can do more than one thing. I mean, we can do all kinds of things. It's really limited by investigators and money, because the data there has just incredible. We have the resolution to do fine detail, and we have spatial coverage to do global processes now that unlike anything we've ever had in the past for the Earth. One of the big methane emitters was Turkmenistan, and when this went public a few months ago, it turned out that Turkmenistan joined the Global Methane Pledge. So a lot of these are oil fields, and there may be a pipeline leaking or something. So it points out to where they can go and fix these problems and reduce the methane contribution to climate change.
Makes me wonder what it looks like in the U.S.
What?
Makes me wonder what it looks like in the U.S.
Oh yeah, there's literally thousands of point sources of methane that have been identified, including landfills. Landfills all over are emitting methane.
I'm amazed that you can detect it.
Yeah, it is challenging if you go back and look at some of these. It's a little noisy, and I've seen the full before they mass it out, and there's a lot of single pixel hits. It looks like a snow scene here, but when you have a nice pattern, one of these things that are downwind, then, and they've also done coordinated flights with Avras, so it's higher resolution, and the two are agreeing very nicely. There's a lot of multi-sensor tests to show all of this is correct, as well as multi-sensor tests for the mineralogy and field work and stuff. So yeah, working very, very well. Besides minerals, there's over here on the right, ice and snow. Here's ice and snow spectra, water. If you do any ecosystems work with water or vegetation, the EMIT system works very well. These are EMIT spectra here. These are all EMIT spectra. You can see with the gaps here due to the water, terrestrial water bands. And we're not seeing the gap here for the water because water is dark and this plot only goes out to 1 micron. Now, with extended mission, we're going to cover all of the terrestrial land masses that's underneath the ISS orbit. And this is just coded by different ecosystem types, like green is tropical rainforests, for example. So if you have a project in any of these areas, EMIT data, if you are, certainly for EMIT, it's with 60-meter pixels, it's best for large scale problems, not a very local field site. So, a little bit about the underlying system that's been working for deriving all these, and that's the tetraquarter system. Tetraquarter is on pan, pan.psi.edu, and can be applied. I do need to update it to the very latest expert system, which is described here. But if you don't know what tetraquarter is, it's a system for identifying, well, it's a system for applying algorithms. And the way we've implemented it is we apply spectroscopy algorithms to determine the composition of what is in a spectrum, and with the idea of going for solid surface. So that includes vegetation for the Earth, water detection in the Earth, sediment in water detection, to mineralogy, to ice and snow, melting snow. And there are a lot of advantages. There are some disadvantages to tetraquarter, but one of the advantages is we do intimate mixtures, aerial mixtures, coatings, all kinds of the different things that are hard to calculate radiative transfer wise. We can detect all these conditions in tetraquarter and map them. We have currently defined spectral features out to 4.5 microns. We need to extend into the UV and beyond into the mid-infrared. But we're doing pretty well. We have over 650 reference spectra for the 0.35 to 4.5 micron range. And these are split into different spectral groups because each spectral region and type of absorption in that region can detect different things. So, for example, detect OH stretches due to OH bearing minerals at 2.6 to 3 microns. And you can also do it in the 1.4 micron region. We can do clays and carbonates in the 2 to 2.5 micron region, iron oxides in the visible and out to 1 micron. So every spectral region has its advantages for detecting certain kinds of chemical bonds. And the spectroscopy detects chemical bonds. So now just a few examples of some EMIT data, and these are all tetraquarter standard products. So let me go back one. Tetraquarter puts out an image for each reference spectrum, and it not only puts out an image, it puts out 3 images. And I won't get into the details, but there are different modes of the correlation coefficient fitting process that is done. And so there's in any one image cube, you have 650 plus, potential things to look at to see if you mapped anything. And there's a lot of statistics built to say which things were found in a particular scene, so you can reduce your search. But then, it still became difficult. And so I started building these scripts that put together colored map products. And there are a variety of map products that are done, including down to the individual things that are all pre-stretched, so you can look at them quickly. The whole whole problem is trying to assess everything that's found. If so much is found, we start out with these summaries. So these are summary products, browse products to show you what's there, but they have a standard stretch so that you could compare, you could mosaic these together for a global mosaic or regional mosaic, or you could even compare what's in here and for example in this, and I'll show an example of that shortly, to other planets like Mars. So this particular one shows, these are all summaries of things. So like Fe2 plus minerals, there's a whole bunch of minerals that went into this color, and the Fe2 plus Fe3 plus mixtures. There could be 10 or 20 different things, and we could split those out if scientifically that was important. What I did split out here is, and even these are collections of multiple results. So here's hematite in the oranges and goethites in the yellows, and these are the goethite grain size and the hematite grain size. So again, depending on science problem, you can drill down to what headquartered is finding to get specifically what you need for your science problem. Let me back up. The hematite and goethite are 2 of the 10 minerals that are important for EMIT and the radiative forcing problem. And here's the other 8, and carbonates, clays, and only some clays are included because those are the ones that are dominant in terrestrial arid systems that are dust generating regions. There are other minerals that I wonder why they don't include, but these are from the climate change people. They've determined that they're only interested in these. I think that may change over time because we may show others. For example, iron sulfates aren't included, but there are a lot of iron sulfates out there. In all of these on the right, this one is an RGB color composite, and then the headquartered mineral map on the left. This area is Saudi Arabia, just shows the different geology. Every scene that I've seen has interesting geology and or ecosystem stuff, and I'll show examples of that. Here's carbonates and clays for this arid region, along with the hematites and goethites. Some areas, obviously on Earth, you don't see the surface geology because the vegetation is too thick, and this is an example where the vegetation is thick enough that not much is seen. A few small areas would be seen, but most of it is vegetation covered. So headquartered also, when it detects vegetation, does other things. It checks the spectral type of the vegetation. Vegetation is harder to get exact species because it changes with time throughout the growing season and how much water it's gotten. So trying to do species work is a little more difficult. But having said that, this red type 13 is a vegetation that tends to grow in more arid regions. So there are classes, but not specific vegetation types. The chlorophyll red edge absorption is its position is shown here. This red edge algorithm could also be used for like mapping sulfur on Io, where the sulfur position in the visible changes with temperature. So the applications are general, and you just need the reference spectra to tell headquartered what to look for. Here's a combination of snow. The white on the right is snow areas, and mostly we're seeing, in the drier areas where it's not covered by snow, we're seeing hematite and some Fe2 plus minerals. But in the infrared, we see that there's quite a complex geology of kaolinite and illite is the greens and yellows, and then blues and cyans are carbonates. If you're into ice and snow and glaciers, like Jeff Cardle and I did submit a proposal that unfortunately wasn't funded to study glaciers and snow and melting snow and its potential impact as a hazard. But this shows certainly with spectroscopy, you can see the snow, you can see the water, and the water band shifts, the H2O bands shift with the phase transition from solid to liquid. We have the reference spectra to detect that. And these again are summaries, but it shows snow in the magenta and then melting snow in the cyan blue colors. And we see at higher elevations, the snow is not melting. At lower elevations, it is. And that's to be expected, but here you've got a quantification of that. In a little more detail in another area in Chile, Argentina. Again, the snow that's not melting in magenta into the melting snow, and then into lakes and rivers, and the rivers have trace sediment being brought down from the glaciers. Okay, this is the region around Moab, north of Moab. This is the Green River over here. Upheaval Dome is right here. It might be seen a little better. And again, these are 1200 pixel wide, and you're not seeing the full resolution. So Upheaval Dome and Canyonlands National Park is over here. Arches National Park is here. Moab is just off the bottom of the image. Our Trex rover field site in 2022 operations was over in this area. So here we have the iron oxides, hematite and goethite going into Fe2+ in other areas, and then the clays and carbonates and sulfates shown in this map. Note that there are clouds in the image and they just come out black because there's not mineralogy. Let me go back to this one. Around cloud edges, sometimes there's multiple reflections between the ground and the clouds, so you can get what in the clouds look like minerals, but that's a multiple scattering effect. There are cloud masks that you can just mask this out and ignore them. Now, this is the EMIT 8 minerals that have absorptions in the infrared. And just to illustrate, so these are summaries. If we look at the muscovites only, and the muscovite absorption position changes with aluminum content in the octahedral structure. So we can look at the high to low iron in the substituting in into the muscovite. So depending on your science problem, you can do some pretty detailed chemistry. We've used this effect here to map faults and fault offsets. Now I'm going to show, this is again the same image with the same tetracorder running on prism data. Here's a prism scene. So this is, note the key down here is the same. So this is a particularly interesting scene for the visible near infrared for the iron oxides. Most Mars scenes aren't this colorful, aren't this diverse in mineralogy. And but if we look at the infrared, we see a different story for this scene. There's hardly any clays or carbonates, well, no carbonates, a few red, that's the montmorillonite group. So there's some very small trace amounts of montmorillonite in this Mars scene, but not much else. And most of this other stuff is just noise in the prism data. But if we look at other wavelengths that we can't see in the EMIT data, this is the 1.9 micron absorption band. So this is showing water content in the minerals, and the wavelength position along here correlates to some mineralogy. For example, these longer wavelengths tend to be sulfate minerals, not uniquely, but if you use other absorptions, you can pin down which mineral it is. And we have that information. I'm just showing you one example here. Then one other example, this is the same tetracorder that would try and map vegetation and everything, the exact same tetracorder run on the moon mineralogy mapper data, and this is the OH fundamental stretch at the 2.72 to 2.83 microns. This is in a paper that is in review. It's been revised and submitted. We hope to get our acceptance here soon. But you know, this shows the incredible diversity on the moon, where, you know, a few years ago, well, a little over a decade ago, nobody thought there was any water on the moon. But it's turning out to be quite complex. Now, at shorter wavelengths in the 2 to 2.5 micron, or 1 to 2.5 micron region, it's very difficult to see any of these. So we have to work out at the 2.8 micron region where the absorptions are stronger. So conclusions, EMIT it's on the space station. It's working great. We have the go for 3 more years, and if we're still going and producing great results, I'm confident we'll have a very long mission on the space station. Note that because we're on so long, we'll have repeat coverage. So people doing time studies, like especially glaciers melting or ecosystems, there's going to be a great data set as we move forward. And there's already a lot of repeat coverage. Right now, I've never seen an imaging spectrometer this well calibrated and with this high a signal to noise. So it's certainly the best currently in space, and I think it's the best that's ever flown. The atmospheric corrections, the JPL team has really come up with it's a very complex system that takes hours of CPU time to run per scene, but they have so many CPUs, they can push the data through and doing the atmospheric corrections, and they're producing just excellent surface reflectance. So there's radiance, reflectance, and some of the touch quarter mapping products are delivered to the AROS data center very quickly. And to get all the data products, you'd need to download GitHub, or for PSI people, we can have it set up on PAN, so you can run touch quarter on PAN. For not just EMIT, any imaging spectrometer can be done. And with that, I'm going to stop this. If you go to search.earthdata.nasa.gov, that's the AROS data center. The key to find EMIT data is to first narrow the search, then go to instruments. Let's see. No. View all instruments. Then go down to EMIT and see how many instruments there are on this. And then you have a choice of reflectance, the calibrated radiance, or, oh, this is new, I haven't seen that before, the plume complexes. So that's the methane. And there's also the uncertainties, methane enhancement data, and they're getting a lot of new stuff, but that's all new in the last few weeks. And then the spectral abundance. So normally, to do abundance from spectroscopy, you've got to run a radiative transfer model. And the typical radiative transfer model is prohibitively complex for deriving abundances from a reflectance spectrum. But I derived some new, using the restrictions of only a few minerals in arid regions, and we could apply this to Mars with some restrictions. We can derive abundances, and I derived a new way where we can get the abundances within a few minutes of CPU time per scene. So it's really well, and that's in a paper that's in revision now, but it's looking very good. So I just wanted to show you the surface reflectance. And if we go, I wish the NASA PDS was this simple. So I'm just going to zoom into Tucson here. And we click a little region of interest and check around Tucson, and we can get the scene. And then if I logged in, you have to log in or to download it, but you can download all this stuff for free. And every pixel here is a full image cube or full spectrum. So this is an image cube full of spectra. This is just a RGB browse product, but gives you an idea of what it is and how easy it is to find the data. And with that, I'll take questions.
Oops. Pretty amazing, Roger. You know, I kind of feel like we should have a link to get to some of this stuff on our page, on our web page.
Sure, we can do that.
That's really neat. So I could like call up Tucson and see what we got in the neighborhood.
Yeah.
You know, I am, you know, I don't know what the sampling is of the ground, but you know, our people, it seems to me people could use this for agricultural monitoring of crops. I mean, because we got huge crop fields.
Yes,
and,
yes.
Did you know what's planted? And so probably know, yeah, you could. I wonder.
Yeah, I didn't
that.
show that, but if we go back to the slideshow, current slide, and go up. Yeah, so over on the right here, in the above center here, those are crop fields near the town of Green River, Utah. So yes, and you know, this is not full resolution, so we're about probably half or a little less than half. So these would be double the size. So you certainly have enough resolution to see what's going on in a crop field. And I mean, what I haven't shown is while we do vegetation and the red edge and the spectral type, we also do the water content of the vegetation, all as standard products.
And how many, I mean, I don't know how often you scan this area, you know, to what, you know, resolution or you know, but do you, are you getting it like several times a day so you can monitor it?
No,
every day.
See, we're trying to do global coverage, and
right.
So it's typically more, can be months apart, at least weeks usually. There's a new system that is on the drawing boards called SBG, Surface Biology, Geology, I think it is. That's going to be, it's the next generation of this imaging spectrometer. It'll have a wider swath. I think it's 30 meters per pixel instead of 60. And it's a repeat every few days of the entire Earth. It's an incredible amount of data.
Oh my God.
Yeah.
Yeah, I mean, I could imagine, you know, people interested in what's going on with waste pools, you know, associated with mines, and do you see leaching of stuff in nearby rivers or something after there's a rain, and where you'd have actually the ability to independently on some time scale monitor things.
Yes, absolutely. And we've shown that kind of stuff with Avarice over the decades, that all of this is possible. So yeah, we just need the system. So, you know, if you're a mining company with big bucks, there are commercial instruments that you can buy that, you know, $50,000, $80,000, and you could fly your areas as often as you want and at much higher spatial resolution.
Right, but that's as you want. Norbert.
Yes, so my question is actually about M3, which you showed here. So I saw on this map there's no more systematic latitude dependence of OH, and to what extent can you distinguish between OH and H2O, and the donor variability is not there, I suppose. And can you just summarize your main results of this paper in review?
Well, I have not seen, so my job on the team is the touch quarter aspect and the full resolution data. I have yet to see, if we go back up to, let's see, yeah, this and this.
No, sorry, I meant M3.
Oh, in M cubed. Okay.
MQ, yeah, the moon. Sorry.
Yeah, let's go back. Okay. Yeah. So if you look at this, the let me go back to full scale. Yeah, there is a latitude dependence of, but there's also there's several effects going on here that make it complex. And one, you see the blue versus the yellow red, and the blue is the basalts. So the basalts have a different OH than hydroxyl band position than the feldspars, the Highlands material. So you have that effect, and then there is the effect of latitude. As you go to the poles, there's more, but the poles tend to be more Highlands material, so you know the color doesn't change there. And notice that these differences, from yellow to red is 0.02 micron band shift. So it's a very small band shift. And how real that is, we really need a higher resolution imaging spectrometer to go up. And then another factor is you see striping of different orbits, and the different orbits are that you see differences. For example, around Copernicus, there's this central region of Copernicus here has a lot of hydroxyl and also water content in the inside the crater. But we see you know, this color here and then a blue. So there's a band shift between the two different orbits. Now, those different orbits are different solar incidence angles. So M3 is only looking nadir, but the incidence angle is changing with different times of day. And that was initially thought to be, and is still, the science community still believes that there's a diurnal dependence. But part of the problem is the surface of the moon is a layered surface. So the topmost layer, you know, the top millimeter, even fraction of a millimeter versus 2 millimeters versus a centimeter, is changing in either composition or grain size or both. And this is an argument for maybe there's a compositional change with as you go lower down or deeper, the OH is at a different band position. So there's different OH bearing minerals in the top different layers. So these effects have to be sorted out by the science community, and it would surely benefit by a higher resolution imaging spectrometer like Trailblazer that's supposed to go up later this year or next year. I forget exactly when launch is.